All right, so can't remember where we are. Source, course, list.
I'm just getting some lime. I'm still listening to you.
That's
Keep
right.
going.
I knew I had about 2 minutes to convince you, and after that, I was no shot.
No. Yeah, I just need some.
Thanks for sticking around for the. I mean, that's what more can I ask?
For the module loading credits rolling. All right, I'm back.
Okay, so so just for context, we're dealing with this guy here. This little data type. I'll even bring that bigger. All right, we got this.
We're making a
list.
new list. No, we're making a list type or type class.
Just straight up type.
Just a type, and it's going to inherit from or be a member of the type class of an equal or whatever it's called.
Oh,
and
to
then
be the deriving.
orderable.
Yeah, we're gonna derive the ord and the EQ type classes. But if we said, okay, because we think about types, right? When we think about types in Haskell, we think about how do you construct a type? How do you build this thing? Well, you got a little shovel, you got a little axe. What are you using to construct these things? And in the list case, there's only two ways to construct a list. Either you use the nil constructor or the cons constructor.
Mm-hmm.
So if I said, man, I wish it's a long time to wait, but if I said, let me just also just try one more thing quickly. I'm just going to pull out that. Okay. So if you see, I'm trying to kill this. Bear with me.
No worries.
7, 8. Can you say, if I do that, can you see that? Is that all right?
I can just see a prompt in the REPL.
You can't see the back and forth?
Just do that again. Yeah, I can see that you're switching between the two tabs at the top, but the content of the window doesn't change.
Content of the window.
So
as in, like, right now you're seeing it compile, and now it's like nothing?
Prompt. Yeah.
Yeah, perfect. Okay. So we're going to keep this one that's going to be our prompt, and here we can edit there.
Is the problem that with the recording the tabs don't work but windows do?
Yeah, tabs don't work, which is, you think the opposite would be true. You think that tabs would work, but a different window wouldn't work. So we're at a data type, right? And we say, okay, cool. Two ways to construct it. So there's a function. Well, in the case nil is kind of the best way to think of nil is it is a function that takes no arguments and gives you something of type list. So if I call nil,
it does. Okay.
So if I call nil, I get something of list t. Even though nil's a value, but it's a value of list t. But you can think of it like it's a function with no arguments.
You didn't define nil. That's something that's
we defined that for the.
Oh, we define it. Okay.
For the list, so we say there's nil. It's a nil or there's cons. So the other function is cons, and it's defined as I take something of type t, something of type list of t, and I give you something back of type list of t.
Yep.
So it's really saying, like, all it does is just kind of smacks it onto the remaining. So it takes the t, puts it into list of t at the top as the head.
Well, we don't know that. We don't know that from the type declaration, though. We just know that it takes an item and a list and returns a list.
Exactly. It could put it on the. It could put it on the tail. It could put it at the end of the list. Yeah, you don't.
Or it could replace something. Or we don't know. Yeah.
But if you look at implementation, we can see that all it does is it recursively constructs itself by using t as the first argument, and then the list of t. Rather it just says, you're right. This is actually quite a weird thing, right? Because that is true that we don't know, but with a value constructor like this, there is no implementation. That is the implementation. Like, just defining the types is the implementation.
I see.
So it's kind of like what you're really saying is the first thing is a T, the next thing is a list of T. If I was to like interrogate the list of T, it might be a T in a list of T. And then it might be a T in a list of T, and it'll be like this tree structure.
Yeah, okay.
But it's just, that's when we think about when we think of lists, it's like to deal with lists, we've got these two value constructors. And so last session we did the product, but we're just going to have a crack at sum. So the goal of sum is we've got some list. In this example, we've got a list 1, 2, 3, and we just want to sum up the elements in the list, the numbers in the list.
Okay.
So I've got this function called sum, takes a list of int and returns an int, namely the sum.
Sorry, just one question. The reason you're using that different notation of cons, like colon, full stop, is that's our implementation of cons. That's not the Prelude one. Okay.
Yeah, cause exactly. Like this is just like to fake the cons in the center and lib. I think other people will do it like they'll say cons instead of using an operator like that.
It wasn't taken, that function name.
Exactly. Okay. This is all custom. We're in the rolling around. So got sum. So we know we take a list of int, return an int. So if you kind of think like this, we've got a list of int, and we know there's only two ways you can construct a list of int, right? Mm-hmm. It's either nil, or you used cons with some element x, and then you've got the rest of the list, which is x's.
Yep.
And that's okay. Let's keep it like this. Yeah. So in the case of nil, what int should we return?
Nil.
Value. Well, it has to be a value of type int.
Oh, I see.
So if I call sum of nil, what would I expect that to return?
It has to be a value of type int.
It has to be a value.
So will it be just the value of the...
So if I've got no things to sum, what's a potential value? What's a good candidate value to represent the sum of
0?
I like it. 0 sounds good. Now it's funny because this, like, sometimes it's harder sometimes to try and work what this is out up front, because it doesn't make any sense really to talk about listing, summing an empty list.
Yeah.
Because theoretically, the sum of an empty list could be any value. It could be 10, 20, minus 1,000. Like there's no, because it's nothing, it could be anything.
Yeah.
In that kind of context. But it turns out that 0 actually is quite handy as the definition for an empty list, because it lets you do other things, which we'll see.
Okay. So
that's the nil case. That's great. We're halfway there. The other case is the cons case, right? So we have to sum up. Somehow we got x, which is, we know x is of type t, or rather, sorry, it's of type int, and x is of type list of int.
Yes.
So if we just like threw in a hole and just said, okay, I got really no idea what I'm doing, let's just see what we've got. It would say some have different, some. Oh, totally. Let's go wrap this up, otherwise it thinks it's different. Cool.
Oh, I see.
So we've got this hole here. It says, all right, Haskell says, hey, I found this hole. What do you want to do about it? And it says, I found the hole, and that hole has to replace something of type int. And it says, there's an expression, here's some bindings. This says, here's what's in scope. You've got x's, which is a list of int, an x, which is an int, and you've got this function called sum, which takes a list of int to an int.
Gotcha.
So it's kind of like that's what you've got to play with. That's all the characters in the story, and how are you going to get an int from that makes sense? So
yes, I know how.
How? Tell me.
You're going to go x plus the sum of the x's.
Too easy.
Is that true?
That's it.
Yeah.
Right? And you can look at this, and even if you were, if you didn't get it that quickly, you could think, all right, well, it's x plus something. I know I take the x,
Yeah.
I've got the x, but it's x plus something. I don't know what the other something is. You could throw a hole in there, right? And ask Haskell again. Haskell says, well, I found this hole here. And this has to be of type int because I've got an int on the left-hand side.
Right.
And it says, so you've got this hole here, and you need something. It has to be an int. So, and here's the bindings that you've got. You've got x's, which is a list of int, x which is an int, and sum, which is a list of int to an int. So it says, how can you, with that, how do you get an int? And you look and go, well, okay, interesting. I have x's here, which I haven't used, right? I've used x for the left-hand side of the expression. So I've used that information, but I haven't used x's. And I have a function here called sum, which given a list of int, which x is a list of int, gives me back an int, namely the sum of that of the x's. Gotcha. And then you go, you don't, well, you go.
I was going to say, and you wouldn't really use x's because you know the whole needs to be an int. And if you use x's, it's not an int, it's a list of ints.
Yeah,
so
exactly.
It can only either be x or sum.
If you naively was like x's, it would say, Haskell would say, hang on, you're trying to add an int in a list of ints. And it would say, actually, there is a function called sum, which you're defining, that given a list, will give you back an int, the sum of that list. So that's it. So if we jump in there, give that a reload, and we say sum of nil, 0, looks good. 1, 2, 3, nil, 6. Beautiful. So here, if we had, say, 5 for nil, or let's say 1 for nil, then when we did this, we'd be off by 1.
Yeah.
So you can kind of think of it like we replace nil with 0. And because
It's
0
almost like an accumulator.
Well, the property here that makes this work is that 0. So we're talking we're in addition here with integers, and so nil is the fancy name is I think it's like it's the additive identity for integers.
Okay.
The idea is that if you take any integer and you add 0 to it, you get back the integer.
Okay, I gotcha.
So it has this nice property that, I can always include it as part of the sum and it has no effect.
Does the identity thing, like say an identity function, does that mean it just, if you give it a value, it returns that value back to you?
Yeah, like say the ID of 5 is 5.
Okay.
You could say, I could implement ID, how would you implement ID for, well, this is if you were thinking, I had to implement an ID for integers specifically, not for every type. You could say ID of int equals x plus 0.
Yeah, okay, gotcha.
And then ID int of 5 is 5.
Yeah.
So it has the property of it's like the use with addition, it becomes the identity function.
Yeah.
And that's kind of like if you look back at the product one we did last session, 1 was the identity for multiplication. Same game. It's like you give me a 5, I times it by 1 and give you back a 5.
Gotcha.
So you can do this all day. So this is the recursive definition of sum.
Yeah.
And it turns out that there is another way to define this, which, it's this whole list module, first you get kind of, used to recursion, but then they're really wanting you to use another way of thinking about implementing these functions. And that's namely to use foldLeft and foldRight. So at the start of the module, they've defined where is it? They've defined foldLeft and foldRight. Now, this is like one of the most amazing things about foldLeft and foldRight is that you can know how to use all of foldLeft and foldRight without ever knowing how to implement it. There's like a way to think about both these implementations, or both functions, foldLeft and foldRight, that kind of let you do everything you can do with it. And so foldRight is a function. If you just look at the type, it's a function that takes it's a function that takes a first argument's a function, A to B to B, second argument's a B, list of A to B. I mean, you don't really get a feel for what the hell's going on by looking at that. But instead, if I told you that foldRight is actually doing constructor replacement. So if we take the list 1, 2, nil.
Yeah.
If I said foldRight, right? foldRight plus plus 0 and this list here.
Yes.
It's called X's. Right?
Yeah.
So I've got the first argument's a function, and plus is a function that takes 2 arguments, A and B, and returns B. We've got 0, which is going to be the B, and a list of A, which is this list here, a list of int.
Yeah.
So that fits the match. But what foldRight does is, so that's kind of like, we can think of it like we've got a function, we've got some initial value, if you like, and then the list.
Yeah.
But what foldRight does is foldRight replaces. So if I just get that there, and maybe just want that again. What foldRight does is I'm going to replace nil with what you passed for the second argument. So I'm going to replace nil with what you passed me. I'm going to replace that constructor. Because remember, nil is the constructor. It's the constructor that gives you a list of T.
Yeah.
And it has to be the last thing because that's how you get out of the recursion. It's the base case.
Yes.
And then it takes this function, and notice how cons takes 2 arguments, right? It takes some element and the rest of the list, or rather, some element and the rest of the list. So a plus in this case also takes 2 arguments. It takes an A and B and returns a B. So what it does is it says, okay, I'm going to replace, maybe I'll come here, I'm going to replace cons with your function.
Huh.
Whoa.
Huh.
And that's all it does. That's all foldRight does. Semantically, it looks at your list and it says, all right, I'm going to take what the first argument, I'm going to replace nil with that, and I'm going to take the second argument, the first argument, it's a function, I'm going to replace cons with that.
Could you write that in, what's the opposite of infix notation again?
Like in prefix?
Yeah, could you write, say, if you yank those 2 lines
Well, you want to write
and
like
redo them? Yeah, like what would it look like written out? What does a list look like when you're not using infix?
Yeah, it looks like this.
Notation.
1 to a list of 2 and nil, and that's, so when I have 2 is going to be, no, that's right, I can say that. So I can say cons takes something of type X, or something of type T, which is the 1, an int that has the value 1, with a list of int, and the list of int here says, all right, cons is 2, a value with a list of int, which nil is list of int, and it makes that as a list. So you can kind of think of like that happens.
Yeah, okay, that helps me kind of understand it, because then that nil, because we know that nil is a type, is a list.
Is a list? I mean, it's weird, but nil is of type list.
Yeah, but we need that to, like you're saying, that we've got to have that type there to attach our the ints that come afterwards. It's got to be
Exactly. Like
glued onto that to
we
a
need
list.
nil as a we need the nil value
Yeah,
to be
to
like
sort of start the chain.
starting point.
Yeah. Okay. Cool. And then cons kind of pairs them up, and then it pairs up the next one with that pair. Yeah. Okay. I gotcha.
Well, actually,
and then so foldRight's just
you go.
Replacing the non-infix version. Well, just for my own
Yeah.
to help me understand. So like line 91, when you do foldRight, it's just replacing that with a plus. With function, which expects two arguments.
Well, sorry, and nil is going to be 0.
0.
Exactly. Yes.
Huh. That's really cool.
So that's the amazing thing is like you take this data type, which has two constructors, this inductive data type has two constructors, two value constructors, nil and this recursive one, and you just go and it just goes and basically changes it. Now, you can think of like if you look here on 94, there's actually there's what do I want to say? There's a associativity, right? So this happens first, and then this happens.
Yes.
So just like when we change it. Exactly. So we get this. That's kind of what's happening. So same thing, it's like first you've got to do the furthest right, and then you start moving outwards from there. And so that's really like there's not really nothing more to say about foldRight than in terms of that, because I mean most of what makes foldRight so powerful is that you can implement so much of the utility functions for lists just using foldRight, and it's changing the F and the B to be whatever you need it to be semantically. And you can always play this game where you go,
okay, I see.
You can always play this game where you just like write the list initially and then see what would I have to do to nil and cons to make it whatever function that I want it to be. You there?
Yeah. Just taking it in.
So this is this is the holy grail of lists. This is like the, that's foldRight, and foldLeft is basically a for loop. How you would think about it as a for loop. So foldRight constructor replacement. foldLeft is more the traditional sense of if I say foldLeft, then I'm more thinking about I'm like your mental model is I'm going to do a for loop where I'm going to start at 0 and then I'm going to look at the next thing in the list. I'm going to add it to 0 and I'm going to accumulate the result in that sense.
So is when it says foldLeft, is that interpreted as fold from the left and fold from the right?
So this is the really weird thing where they both fold from the right.
Okay.
So I just use the name, but they're both right associative is what I should say.
Right. But if I have like an array, it's not the right word, I know, but okay, our list. I guess conceptually, foldRight starts at the end and works back, and foldLeft starts at the beginning and works to the end, or is that not the right way to think about it?
Well, it's funny because once you get into the details, and I'm just thinking of like, I think it'd probably be worth like having a whole just session on how does foldLeft and foldRight actually work, and how do why are there two different ways of doing something that feels like the same thing, and there's actually another version of foldLeft which is like a strict version. And there's a lot of quite interesting things about because there's foldLeft, foldRight can work on over infinite lists, foldLeft can't. So it's kind of there's a lot kind of like that we can jump in and play around with there. But I guess almost as like an experiment too, I just want to see if you just have the mental model of constructor replacement,
Mm.
and foldLeft is just a traditional for loop, how far can you get with just that mental model?
Yeah.
So I definitely plan on like coming back and just spending like a whole session on covering how these
Okay.
things work internally and why is it implemented like that? Like how did we get to that point ourselves
Okay.
instead of just taking that for what it is? But if we kind of take that,
Just take it as given. Yeah.
take it as given, take it as like God gives you fold left and fold right, and says
Yeah.
you can't look any further. That's atomic. Was it quark? Less than an
quark.
atom? Quark?
Yeah.
It's a quark. We don't know any deeper than that. That's what we've got to think for right now.
Okay.
So now if we come back to sum and we say, we know that was correct. So we come to sum, we go, look, with Herb, we just learned about this fold left, fold right business.
Yes.
How is there a way we can implement sum using those functions instead of recursively? Now, one of the problems with doing a recursive definition is that it's expensive, right? We've got to do a recursive call every time. And I mean, in this case, Haskell could optimize it with a tail call recursion elimination. But generally speaking, yeah, there's like a kind of I don't know, there's an ease to it to fold left and fold right once you start using that as a tool that you don't have to think about the intricacies of recursion. So let's say we didn't do it recursively. Let's just say we're going to do it like this, right? Now, I'm going to say that we can do everything we need to do by just looking at the list as a whole. So let's take, so if you think about lists, right? I was thinking about sum, exactly what we were doing before, right? It was, you have 1, 2, 3 here.
Mm.
What we want to do is we want to think as this list of 1 to 3 as replace nil with 0.
Yeah.
And then replace cons with plus.
Yeah.
So how do we, if I get a list of int, how would I, if I'm here, how would I use foldRight? Let's take foldRight, for example, to implement sum as opposed to recursively.
Well, I guess you would just give it, it takes a function and an initial value and a list, right? So you would just go, yeah, foldRight, the function, initial value, list. The function will be just plus.
Plus, yeah.
The initial value will be 0, which will substitute. Well, I don't know. Okay, I'll find out. And then the list, which is your x's.
X's. Bang. So, all right, that looks pretty good. So,
Is that?
how confident are you?
I mean, in general, about myself, very low. But about the answer to this question, 79%.
That's good. I mean, that's much higher than your average day-to-day
Well,
confidence.
the rest is reserved for self-confidence. 21%. All right, let's see.
Bang. Love it.
I'm up to 22%.
20%. We'll be 99% once we get into this course. Now, one of the beautiful things here is notice how we kind of grab a binding for the argument, right? But then we just pass it as the hit me.
I learned this morning.
Oh, really? What are we going to do?
Because of partial application. If we say foldRight, give it a function, give it an initial value, and don't give it the list, it's just going to return a function that's waiting for a list because we haven't given it all its arguments. So we can just omit the x's variable on the, or reference, whatever you call it, parameter on the left and on the right. because sum will then, therefore, it's the same thing. Sum's going to be waiting for one more input, which is the list, and so is foldRight. So like
Exactly.
it's the same thing.
And so that, I couldn't have said it any better myself. Like if we take the x's and we do the lambda kind of conversion,
Yes.
you know, sum is really this. You know, it's a function that takes x's, and then it's like, exactly right. I can partially apply a foldRight with plus and 0, and then at this point, I'm just waiting for the x's.
Yes.
So I can say, well, hang on, well, I'll let someone else go and call me with the x's. And so that is their equivalent.
Right.
So that's why, like, I guess the beauty of foldRight here is that's a definition for sum.
Yes.
No pattern matching, no handling the base case, right? There's less work, there's less moving parts because you've kind of abstracted away the machinery of the recursion.
Yeah, and that's just because because whenever you emit a parameter, a value for a parameter, it's just going to partially apply it. And
Partially apply, give you back another function. All right, I'm ready for the x's.
Constant currying.
A lot of currying, curry. So, I mean, actually, I had some curry. I just had some curry then for lunch. I was getting ready for I finally ate
currying?
that. Not yet. Not yet. I mean, fingers crossed. I mean, I think I'm going to have curry again tonight as well. So I'm going for the double curry. Nice. I've gone for the double application. So not so easy is, so some, seems kind of, a bit more straightforward to work out how do you get from, replacing the nil and the cons. Now we're going to do length. So length is kind of does what it says. It says, give me a list. I'll tell you what the length is. So here we've got list 1, 2, 3. It gives you back 3. How do you feel about that? Does that? We're going to implement this function called.
Yeah. Okay. Because nil, the value of nil will be 0. Okay. Yeah.
So now we're going to play the same game. What do I have to replace nil with, and what do I have to replace cons with to implement length?
Okay, so let's think about that.
Sometimes I would say, think about the empty list. What would you replace nil with just by itself?
That will be 0.
0, okay, that's good. So you kind of feel like you put 0 for nil, that would make sense. Now you got to replace cons with something.
Oh, this is a good way to think about it. Yeah.
Well, I'm trying to think if I remember what it was. I mean, the other thing is you can think more abstract. So you could say, I know I'm just going to replace it with some function that takes an a and a b, or an x and a y.
Yes.
And then does something, right? So we can.
Yes. Okay. So the as in cons will be replaced by that function.
By that function, yeah. So we can do more complicated things than just, something simple like add or time. We can do any function that takes 2 arguments and returns something of the same type.
I think what it'll do is just add 1. It'll take, so in the example above, we've got 3 and 0. So if x is 3 and y is 0, you just want to add 1 to 0.
Yeah, okay. Yeah,
so you'll be 1 plus y, and you'll actually ignore x. Doesn't matter what the value of x is. You just want to know that there was an x. And then that will return 1. So when you go to the next step, the next set outside, you'll be adding 1 to 1, and you'll get 2.
That is music to my ears. So let's try that, right? So let's say we're gonna define a function called accumulate. Oh hell, we'll just put a lambda in there.
Okay, so yeah, that's good.
We'll say takes a x and a y, and we'll just leave that for a second. And the initial value is 0.
Yeah. And
we said we don't actually. Can I do it like? That's going to give me a tuple. Oh yeah, I think I can do that. Or can I?
Yeah, what is it going to give you? How
Well,
does that work?
I mean, I could do x, y like that,
Oh yeah.
but I'm pretty
Yeah.
sure. I'm pretty sure. We'll see in a sec. I'm pretty sure you can wrap that up in a tuple, and that will. That's like the two arguments.
Maybe.
Like I'm pretty sure.
I've never seen that, but
I'm pretty sure that
it's
is
the same
equivalent
as
to.
lambda x, lambda y. Return.
That's the
Okay.
decurried
Cool.
version, right? So that's the
Right.
curried version. That's the decurried version. And
Cool.
when any say JavaScript, right, where I call like, I don't know, like some function, like a function a b,
Yeah.
say add or something. Hey, kidding. I have an add a plus b, right? We're in JS land.
Yeah.
The arguments are a tuple of
Oh, okay.
of values. So that's that's like in Haskell land, that's a decurried function where you've like
Okay.
you've kind of uncurried rather all the arguments into
Yeah.
like one tuple, that they're there,
Okay,
they're
I
all
see.
there, as opposed to just some being there.
And
So,
so for that reason, if you pass a different number, like a, yeah, I understand. Like
So if
it's
Haskell-
expecting two arguments.
Exactly. Haskell sees this and goes, "Ha, nice syntactic sugar. I'm going to de-sugar that into a lambda that takes
Yeah.
an x that returns a lambda that takes a y."
Yeah.
And so we said 1 plus y feels good, feels right.
Yeah.
And I would be surprised if
Well,
I still like it. Couldn't match
is it a x comma y? No.
a list of a. I might have the order off. Maybe it's. Oh, sorry. So I forgot to mention foldRight. If you look at the arguments of the function,
Okay.
it's going
different.
to be that's going to be the right thing. That's going to be the left thing. Which actually that should be right. I know that we're going to replace this to x. It's going to say it's fine, and I'm not going to like that. Okay, it didn't. Good. That's so it's not that. Is it the fact couldn't match? So it says couldn't match type A with int to int. B. No, let me reload. It says couldn't match. Wait, it's still saying x. All right, let me just be 100% sure that I'm doing the right thing.
Okay. No. Oh.
All right, so disregard what I said about it being syntactic
Okay,
sugar. That's actually saying you need a tuple, not
It needs to literally be a tuple.
it needs to be a tuple of type. Yeah. So, but there is or maybe that's syntactic sugar for.
No brackets. No,
There's
doesn't like
there's a
either.
way to do this. I don't
know what it is either.
It's doing
I mean,
okay.
That's not
let's keep-
surprising, is it?
Oh my god! I swear it was. Anyway, that's suffice for now. Okay, so does this work? That's the main question. Does it work? 42. All right.
Yes.
Length.
Roll credits.
Give me that one.
I think you just put a space, not a comma. You want to try that?
As in like that?
Yeah, like that.
Ooh.
Like that. I think it's that.
Ooh. That feels good.
Does feel good, doesn't it?
Oh no,
No,
that's fine.
doesn't.
That's fine.
Is
No,
it?
it's just because I never.
Oh, that was a warning. Oh, okay. I see. You need to ignore the.
Dave.
Here we go.
Dave, next week you're doing the sessions. That is
No.
on point.
Leave me in my ivory tower.
So what are we saying here? We're going to say 3?
Yes. 90%.
3. Oh,
That's
look at
so
this.
good.
3, 0. I love it. That's
Cool.
it. And so So this is the that's great. I mean, that's exactly what we need to do. So there's this kind of there's this style, which kind of to me always is more intuitive to look at that and go, oh, you're ignoring the first argument, you're taking away, adding one. Now you have the point free style, which is the idea of like we don't want to have to name arguments. We can always compose or like glue together functions in a way that we never have to actually see the internal workings of the function.
Okay.
So there's another way to implement this lambda here.
Okay.
And namely, it's const 1.
Oh.
I'm pretty sure.
So that just returns a 1?
Const? So const says I take an A and a B and I give you back an A. So I ignore the second argument.
Okay.
So in this case, we're saying I'll give you 1. Or maybe, no, what am I,
Is it const y?
No. Well, I can't have a name.
No.
And I'm pretty sure it's const 1. Because you can go, no, it can't be const 1. What am I saying? It takes an A and a B and turns out A. I kind of want to embed, well, no, I want, if I give it 1, that returns a function that's going to take a B we're going to ignore. So that's not, in this case, we can think of...
You want to add...
Could be that you just go...
So you want to add const 1 to the return to the initial value? Oh, I don't know.
Yeah, okay, I see what's going on here. So what we're going to do is we're going to pass const a function.
Yes.
That
it's waiting another argument.
It's waiting its last argument, right? But then const is going to take, so this is, I mean, it's really weird because we're talking about A's and B's, but in this case, A is a function. A has a function type A to B, right? Like it's kind of like if you replace A with,
yeah.
Because you pass it a function that's just waiting for one more argument and you get back a B.
Yeah.
And then B is going to be, actually still kind of shocked that worked in the sense that we know that this function here has to be able to take 2 arguments.
Const takes 2, but so does plus. So you're going to give... So what does const actually do?
I mean, const is just like... If I say const 1, 2, it gives you back 1.
Oh.
So it just takes the first argument. It's just a function. It takes 2 arguments and returns the first.
So can you say like const? Can you say like const true 7 and get true back, or does it have to be an integer?
I think they got to be the same type. Oh no. Okay. Look at that.
So it's almost like a test for like, yeah, if a second argument exists, it will return, or when a second argument exists, it will return the first argument back to you.
It will wait till it's called the second argument.
You need to give me that second argument, and then you get back your first one.
You get the first one. So in this case, you're saying
it's awaiting the second.
Yeah, you know what it's doing? It's saying, oh look, I'll take. So we look at the type again. It says I'll take A.
Yeah.
Sweet. A is just a function that's waiting for one more argument.
Yeah.
Right. Now I'll take the next argument, which will be, which in this case will be the X.
Yeah.
Right. And then, right, it takes the X. Then it says, I'll give you back the original. Right. And then that gets called with Y.
Okay, yeah.
Which is so hard to think about. Like that's just.
Yeah, I'm like on the edge of understanding it, but I kind of get it. Yeah.
like, and I mean, it's okay. It's a nice way of like, yeah. Look, at this point, you never had to. There was no X's or Y's. You never talked about. You never had to give names for anything. It just kind of comes. The list comes. Length is waiting for a list. List comes
Yes.
in. And it takes this function. I mean, sorry, foldRight goes. I'll take this function 0, and I'll start working on the list. I like to begin with. I don't worry about kind of point free, because to me, if I have to come back and read the thing, I'm going to get that a lot quicker than I'm going to get const plus
It's more,
1 and going
yeah,
through.
well, you could even use like, am I right? You could use like a where.
Yeah, exactly.
Yeah, where you could say yeah.
And that's just as handy as well, just to have a name for that thing. So it's just a different style, and it tends to be the more experience you have with Haskell, then I there are times where it is exactly what that little bit, especially when you're doing like function composition. You've got two functions and you're composing them together instead of like having a wrapper function. It can get a bit noisy. So there are times where point free is handy, but you've nailed it. That's really good. That if you understand, if you can understand how to do length, then that kind of gives you a feel for like you can kind of implement these functions however you want. The one that you kind of stick in for cons.
So does point free just mean that there are no variables in your function definition?
Yeah, you'll never see a name for a variable.
And it's always just awaiting the last. Well, of course they only ever take one argument, but like it's just, you're just going to take one argument and just pass it down the chain. You never need to name it. Or
it's this like you're building like a composition, or you're building some function up such that you kind of plug in the argument, and it goes boom, and it just kind of like does all the evaluation.
Scaffold up from that. Yeah. Okay. Cool.
And you kind of always use like little combiners to get all your intermediary functions. And I think you can always do it. I think someone proved that any expression Haskell can always be turned point free. Like you can take any expression and name every function, and you can like plug it into an algorithm, and like a tool will spit out the point free equivalent. So yeah,
that's very good.
I mean, it's interesting. It's definitely interesting that like, there's this correspondence between point free expressions, but I think certainly the natural starting point always seems to be like, I want to name everything, and then slowly take names away.
Yeah, that makes sense. So you can sort of think through it. Hey, we should probably
jump off,
switch over to the other meeting now.
Just bring them into this one.
I was just going to ask a question though, like with this course. So are you just is this an actual exercise that we're working through? It's one of the exercises, yeah? Like these instructions in the comments, did they come, you didn't write those, they came with the course?
No, this is just part of the course that was developed by Tony Morris when he was at Nectar.
Okay, gotcha.
Right. So yeah, this all just exists as a separate thing to
cool.
We're just kind of moving through the flow that is the course.
Gotcha. Awesome.
All right, I think like with that, then we can like now, like after this, it's just like you just implement map and filter and append with reduced writes. But I think next Sesh we'll actually go back to foldLeft and foldRight and try and like get a more of an insight into what's actually going on.
That would be good, yeah. Cool.
All right,
thanks.
I'll wrap this up, and then I'll see you on the other side.
Okay, no worries. I'll just okay, sounds good. Don't record the rest. Talk to you soon.
All right, see you in a sec.